just to clarify then, what we talked about yesterday when we introduced metallic bonding was that I said we're about to launch into a whole series of different sections in chemistry that are going to stage 2, all right? So it's very important that you get the foundation. This is the foundation today for ionic bonding. We just spent a bit of time building some models of ionic lattices, and we'll use that word in a minute when we explain what an ionic bonding is, or what an actual ionic bond is. Just to clarify the types of bonding that we've already looked at. So yesterday we looked at metallic bonding, and when we looked at metallic bonding, you'll recall, for those that paid any attention, then that we had a metal bonded to a metal. And we actually had that, okay, also on the board, and we'll run through that every single time when we look at what's happening in all the different types of bonding. So yesterday when we looked at metals, we had a metal bonded to a metal. And we said metal forms a lattice, all right? And we've actually just had a look at some lattices, but the lattices that we just built just then were actually ionic lattices, not metallic lattices. The difference between a metal and an ionic bond is obviously we've got a non-metal involved. So an ionic bond will involve a metal and a non-metal most of the time. And I'll use that word loosely in a minute. I've talked about it in terms of loosely because it simply involves bonding between oppositely charged ions. So we did talk about ions recently, and so these are under the heading of ions. They are simply a charged atom. Anyone remember how they got charged? Going right back to the beginning stuff on bonding, we talked about that. What happens, Ethan? Good. So the whole idea here, in terms of how chemicals got a filled outer shell, was either a loss or it was a gain of electrons, is what we spoke about. And so we use that theory to explain what causes an ionic bond. And hopefully you'll grasp that when we run through it right now. So cations and anions, and I've got here positive charge and negative charge. Now you would already be aware, hopefully, from your general knowledge, that opposite charges will attract in any scenario, all right? All we're doing over here now is looking at a metal and a non-metal, okay, the actual elements, and we're looking at the configuration for each of those elements as well. So you can see that sodium's got a configuration of 281, and that's just using obviously the KLMN notation. And this is not stable. Sodium, as we've already talked about, wants to get a filled outer shell. Over here, chlorine, same, not stable. Chlorine also wants to get a filled outer shell. However, it's going to happen, all right, in the valence shell for chlorine. We talked about metals being, or having a tendency to lose electrons. So actually what happens when we have sodium metal mixed in with chlorine gas, we produce an ionic compound, sodium chloride. That's how we actually, well, it's not how we make sodium chloride, it's a way of making sodium chloride. The sodium chloride, the stuff that we use, table salt, comes from the ocean, all right? So we take sodium, if we were to make it, sodium metal, we react with chlorine gas and we actually end up with an ionic compound. So they both end up with a stable outer shell. They're both happy at the end of the day, more or less. What we've generated from that is a sodium ion now, because we haven't done anything to the protons in the nucleus. So sodium has still got 11 protons, okay, and chlorine has still got all of its protons in the nucleus as well. Now it's got an extra electron, so the charge has changed, so chlorine now becomes chloride. Now as soon as we've done that, obviously with one atom, every single atom of sodium would have donated its electron to every chlorine atom that it come into contact with, or near, in that reaction. As soon as we get this happen, we get a charge on the cation, positive, and so we get the positive charge, all right? And cat has got positive in it, if you can't remember. And the anion being negative. This is actually the ionic bond that has been formed. That's an example of just one ionic bond. But we spoke previously about the idea of a lattice, and a lattice is a continuous structure. So as soon as we form one ionic bond, you have to consider that there's going to be many, many more bonds formed between all the sodium ions and all the chloride ions, depending on the quantities of chemicals that we're acting together. So what we find then is that every single oppositely charged ion, metal and non-metal, will form an ionic bond. It's a basis of a lattice structure. Now this is only a two-dimensional image, but of course that image will extend behind the board and in front of the board, and so the structures that we've got, that we'll look at in a minute, will form a cubic structure, or we call it a cubic lattice. And so if we were to look at this sodium, for example, that sodium has got a chlorine here, it's got a chloride behind the board, one above it, below, left and right. So for each sodium ion, there's 6 chlorides around it. And our example that we looked at was this lattice structure here, all right? And so what we end up with, although we should have grey, yellow, all the way through, all right, we weren't too fussed about that. What we were trying to get was the idea that a lattice, okay, will form whenever we form an ionic compound. The general term for these are called salts. Okay, so we'll begin to talk about salts, but it's the same as an ionic compound. So we have a metal bonded to a non-metal, bonded to a non-metal, a metal, non-metal, metal, non-metal, all the way through. So anything that looks like this, okay, is under the category of an ionic structure or an ionic compound. In Year 10 we did a whole lot of formula too, didn't we? Okay, we talked about working out ionic formula, and that'll come up next. Alright, so here's one type of ionic lattice. Other groups, okay, began to build other types of ionic lattices as well. Alright? And can anyone tell me why is it that these are different? What causes them to be different? What do you think makes these shapes different, Ethan?
Maybe the amount of elements.
Good, based on what?
The formula for it.
The formula, excellent. So it just so happened that when we did a sodium chloride structure, it was one electron being lost, one being gained. So if we have got 2 electrons being lost, okay, 2 being gained, what do you think that shape would be? No. If it was the same number of electrons lost from one element and gained by the other, are those shapes always going to be cubic?
No. Yes.
They are. It's going to be a 1:1 ratio. Okay? So if I've got, say, calcium oxide, I would expect would have a cubic structure as well. But if I had something like sodium oxide, which is Na2O, 2 sodiums to 1 oxygen to balance out the charge, then it's going to have a different lattice altogether, a different shape, and it won't be cubic. Now, the shapes of lattices will vary. In the sector, there is some images that I just put in. So cubic is the most common, but we can have rhombic shaped lattices, which is like a square on its side. Okay, we can have pentagon shaped lattices, all right, depending on how many positive atoms are bonded to negative atoms. The shapes will vary. We only use this one because it's the simplest version of an ionic compound that we can find. It's a 1:1 ratio, it's straightforward. These are still correct. These still follow the same type of scenario. These are all lattices, okay, but they are simply lattices with different numbers of cations and anions in them. So thank you to all those that built all these weird and wonderful structures. If we had enough atoms, you would see they would form a whole series of different types of salts. Okay, and the only thing we would have needed to have checked, whoops, there's a bit of an error in this one. Okay, we've got 4 atoms that are obviously the same, bonded to one another. All right, so this would not satisfy the criteria for an ionic compound because we wouldn't have a sodium atom next to a sodium atom, next to a sodium atom, next to a sodium atom. It should be metal, non-metal, metal, non-metal, anywhere in the structure that we look for. Okay. Any questions with ionic compounds? Okay, so that was our model for an ionic compound. And next lesson, we're going to look at how we do ionic formulae. Because as soon as you know how to do ionic formulae, you've really sort of like nailed ionic compounds. It's not too complex. Properties, while we're on this. So do you think there's going to be hard or soft compounds in general? Hard, okay. And if you've gone to the cupboard and got salt, okay, it's probably pretty difficult to squash salt in your hands. You can probably get a hammer, you can crush it, but all you're doing is you're breaking the ionic bond, okay, with a hammer. On that point, do you think they're going to be malleable like metals were? No. All right, these are not malleable. There's a physical bond between all the ions. So if I was going to try and break the structure, okay, and that's what it's going to do, if I put pressure on it, it's going to actually break the bonds. I won't do it because it was a beautiful structure that Liam and Ethan made. So if I put enough pressure on it, all right, then that would actually break the bonds and I get a fracture through there. Oh, here's another thing. Which way do you think it's going to fracture if it's sodium chloride? So if I've got a crystal of sodium chloride, hit it with a hammer, what shape do you think all the crystals are going to be?
Squares.
Ethan? Squares. We call that a cubic structure. So all I'm going to do is I'm going to break it across here or here. I'm not going to be able to actually diagonally break, all right, this sort of structure. Now, although we haven't done much on minerals, okay, and their shapes, we call that the cleavage, all right? And if you get a metal, if you get a mineral, and if you didn't know what the shape of the structure was, you hit it with a hammer, and the shape that it breaks into tells you something about how the atoms are bonded, okay? We don't do that anymore with ionic compounds, but just suffice to say, the simplest one is sodium chloride, and it's always going to be cubic. All right, let's move on.